All right. So, good evening, students. I am Anubhav Nath. I am Pmrf from Department of Chemistry at Kanpur, and this is the session three of our Nptel course. This is Transition Metal Organometallic Chemistry Principles to Applications. So, I have already taken two classes on this similar course, and today I have also framed some problem solving sessions, and I will discuss those problems with you. This will actually clear the basic concepts and idea, which will be helpful for you to crack any national level examination, or you can have a clear conceptual idea on this specific aspect. So, I think the screen is visible to all of you. Okay, so we shall start. The first problem in our this session is comprising of this model question that I have framed. This is on beta hydride elimination. So question is the primary mode of possible decomposition pathway that are prevailing in S-alkyl organometallic compounds is or are oligomerization, alpha elimination, beta elimination, or insertion. So the correct option is option B, that is the elimination, beta hydride elimination. So you will encounter about this beta hydride elimination a lot of time. Okay, in your total tenure, you will go through these kind of reactions. Is the beta hydride elimination. So beta hydride elimination is nothing but is a reaction when a metal complex which is bound to an alkyl group, the alkyl group must possess the basic criteria for beta hydride elimination with the alkyl group that is attached to the metal must possess a beta hydrogen atom, one, two, not more than three. So this is the actually criteria, the major criteria for beta hydride elimination. The molecule must possess an alkyl group bound to the metal atom that is having a beta hydrogen. You can see over here, this is the metal, and here this is the alkyl group RCH2CH2. So now this is the alpha because it's directly bonded to the metal atom. So this is beta. So here two hydrogen atoms are there. I have actually shown only one, but there are two hydrogen atoms, two beta hydrogen. So now the second criteria is this beta hydrogen atom should be cis to the metal center. They should come on the same plane. Otherwise, the interaction between this hydrogen and this metal will not be possible. So in further cases, you will see there are a lot of beta hydrogen atoms, but they are not actually cis to this metal center. So then, despite having a beta hydrogen, the molecule will be stable because it will not undergo beta hydride elimination. Here, this is a free alkyl group, and you all know that alkyl groups are freely moving. They can move freely because the rotation around the sigma bond between the metal carbon or carbon carbon bonds are free. That's why these are free, and so this rotation will be free, so this hydrogen can come to the cis orientation to the metal center. Another case is there, if this ligand center, there is a ligand, the other ligands that are bound to the metal center are too much bulky in nature, if they are too heavy in nature, then this ln, the ligand moiety, will not allow these hydrogen atoms to come closer or cis to this metal atom. Then also beta hydride elimination will not be possible. So the major criteria though is the molecule must possess a beta hydrogen atom, but also other factors are also there. I will discuss about those examples in later stages. But the primary criteria being the molecule must possess a beta hydrogen atom. Now this beta hydrogen atom should interact with the metal. Now this interaction is called agostic interaction. So you can Google it about what is agostic interaction. Agostic interaction is nothing but the metal atom is actually having an ion field interaction with the hydrogen atom, and now these hydrogen atoms become polar. Okay, this CH bond is not polar, but now because of the presence of the metal atom, metal is positively charged, there is some interaction it will put a negative charge on the hydrogen atom, that is called a agostic interaction. Now because of this agostic interaction, this hydrogen becoming a hydride gets shifted to the metal atom, and this bond collapses into the alpha beta double bond. So we are actually forming a double bond, that is the olefin. It is an olefin, and we are left with a hydride. So you can see this metal atom has a alkyl group. This alkyl group is a 2 electron donor. You all know from the organometallic examples, like the alkyl group is a 2 electron donor. Now this olefin is also a 2 electron donor, and the hydrogen atom is also a 2 electron donor. So now this is actually 2 electron donor ligand, but it is going to a 2 plus 2, that is 4 electron donor. So the total electron count of the metal center gets increased. Okay, the total electron count on the metal center gets increased by 2. Here it is 2 electron, but here it is 2 from hydride and 2 from this olefin. So 4. So from 2 we are going to 4. So if it is a 16 electron complex, it will go to an 18 electron complex. So this is the basic criteria of an beta hydrogen elimination. A alkyl group having a beta hydrogen must be attached to the metal atom, and after this beta hydride elimination, a metal hydride is formed which is bonded to an alkene. Now, for example, butyl group can undergo this reaction. Butyl group is nothing but CH2, 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 CH3. But a methyl group has only alpha hydrogen atoms, only 3 alpha hydrogens. So methyl groups cannot undergo this beta hydride elimination. So for in later stages, you will understand more because we will be going through several examples. Okay. So here in the second question is one of the ways to suppress the beta hydride elimination pathway in S alkyl organometallic compounds is, firstly, the central metal atom should be coordinatively unsaturated. Second option, choosing the S alkyl ligand without any beta hydrogen. Third option, choosing a very bulky ligand without any alpha hydrogen. And the fourth option being by making the departing olefin favorable. So the correct action is option B, that is the choosing the S alkyl ligand without any beta hydrogen. So firstly, in previous slide, I have already discussed with you the major and the foremost criteria of beta hydride elimination is nothing but the alkyl group such that it has a beta hydrogen should be bonded to a metal atom. This is the primary criteria. Without any beta hydrogen, beta hydride elimination is not possible. So the answer being choosing the S alkyl ligand without any beta hydrogen is the first criteria, that is to suppress the beta hydride elimination in S alkyl organometallic compounds. Now let us come to the other examples. Firstly, I have noted 2 points here. You can note it down. First one is the metal complex must has an empty or vacant site cis to the alkyl group that may undergo beta hydride elimination. So if the metal atom does not have an empty space or vacant site which can actually allow the alkyl group to come to the cis orientation of the metal atom, then it will not allow the group to undergo beta hydride elimination. Just in the previous example, I have shown you if this space is blocked by the ligand framework so that this alkyl group is not able to undergo a syn or cis orientation with the metal atom, then this will not undergo a beta hydride elimination. So the first criteria, the second criteria will be the vacant or empty site should be there where this hydride of this alkyl group can come and interact with the metal atom. The second point is the facile cleavage of the CH bond. So a d electron pair is needed because you see in the first step this is a CH bond. So CH bond is comprised of the sigma homo and the sigma star lumo. Now if the metal atom has to put the 2 electrons into the CH sigma star, that is the LUMO orbital of the CH bond, so that this sigma star LUMO gets destabilized and this metal hydride bond forms and an olefin forms. So the metal atom should have preferably a 2 electron on its head to put that into the sigma star orbital of the CH bond. But if the metal atom is D0, that is there is devoid of any electron on it, then it cannot put this 2 electron on the CH sigma star. So we are coming to the conclusion that D0 metal alkyl compound, there are D0 metals. D0 metals, that is titanium 4, is a D0 metal. These alkyls are generally much more stable to beta hydride elimination because they have no electrons on the metal atom. So they cannot put the electrons into the, they cannot throw the electron on the CH sigma star. So they cannot break the CH bond. That's why for D0 metal alkyls, the beta hydride elimination are actually clumsy or less feasible. But for the other metals, the D2 metal or higher metal olefins, that is the manganese 1 complexes or chromium complexes or tungsten complexes or the iron 2 complexes, these complexes are actually not very much stable to beta hydrogen elimination, because this will put the hydrogen, because these are actually D2 metal alkyls. D2 has some more electron density on the metal atoms, so they will throw the electron on the sigma star or the LUMO of the CH bond, thus breaking the bond and resulting in a beta hydride elimination. So for coming to a conclusion, we have got 2 points. Firstly, there should be an empty or vacant site, that is cis, or in the syn orientation to the alkyl group, that should undergo the beta hydrogen elimination. And secondly, the D2 and higher metal alkyls are actually prone towards beta hydride elimination, but the D0 metal alkyls are comparatively stable to beta hydride elimination. The third complex, I will come to this specific titanium complex example. There are two titanium complexes are given. Firstly, this is titanium CH2 CMe3 whole 4. It is also titanium plus 4 complex. And this is titanium tetramethyl. That is also titanium plus 4 complex. So both are titanium plus 4. Now, from the previous slide, I have told you D0 metal alkenes are less prone towards beta hydride elimination. Now, this is titanium 4 and this is also titanium 4. So titanium is actually 4s2 3d2. So titanium plus 4 is D0. So titanium 0, both the complexes are less prone or reluctant towards beta hydride elimination. But still there are comparison between them, the which one is more stable or which one is less stable. So the options are: A is more stable than B, B is more stable than A, B possesses beta hydrogen atom, or both are relatively stable at room temperature. First of all, both the complexes are titanium plus 4 D0 metal alkyls, and this is a methyl group. So this is not having any beta hydrogen. So the third option, that is the B possesses beta hydrogen atom, is wrong. And first one, that is the titanium CH2 CMe3. You can see this is an alpha carbon. So these are alpha hydrogens. Now this is the beta carbon. So beta carbon has 3 methyl groups, no hydrogen groups. So this has also no beta hydrogen atoms. These hydrogens are gamma from this titanium, because this is alpha, this is beta, and this is gamma. So gamma hydrogen atoms are not actually responsible for beta hydrogen elimination. So both the none of the complexes have beta hydrogen. But I will give you a hint on this. This is a compound. Compound A, it is at a melting point of 90 degrees Celsius. That is a neopentyl ligand. This is just the abbreviated form of this ligand. You can take a note down of it. This is the CH2CMe3 whole Me3. This is a neopentyl ligand. So neopentyl ligand, I have told you that this is absent of any beta hydrogen. There is no beta hydrogen in neopentyl ligand, because this is alpha, this is beta, and this is gamma. And methyl group has also only alpha hydrogen atoms, so it is also devoid of any beta hydrogen atoms. So these I have actually given you information, like the B compound, that is titanium CH3 whole 4. This decomposes above minus 40 degrees Celsius. So this is actually very, very unstable. So above minus 40 degree, this is destabilized. Now, what is the possible reason? Because the melting point of first compound A, it is 90 degrees Celsius, quite high. The difference between stability of temperature is 130 degrees Celsius in case of these two compounds. So the actual reason is coordinatively unsaturation, because titanium is actually tetracoordinated in both the cases. But in case of this compound, this group is quite bulky in nature, because you see there is a 1 2 3 carbon atoms, and there is actually 3 into 3. So there is 3 into 2, as 5 carbon atoms is there, and there are actually 4 such groups. So 5 into 4, that is 20. So 20 carbon atoms are there in the molecule. So around titanium, the environment is quite bulky here, and here there are only 4 carbon atoms present. So around titanium in the B complex, the environment is less bulky. Now the coordinative saturation, that is coordination is quite saturated in this case, but in this case the saturation is quite less, because the group are less bulky. So in this case, since this is less bulky, so there are several thermodynamic reactions that will be degrade this B compound. But since these groups are actually bulky, this will not allow other groups to actually destabilize this titanium. That's why this compound A is quite stable. Its melting point is 90 degrees Celsius, quite high. Actually room temperature, it is solid. But this case, the titanium CH3 whole 4, this is actually less stable. This decomposes only above minus 40. So the actual answer lies in this concept, that is a coordinatively unsaturated, because here the group that are present in titanium are actually quite bulky. These are not allowing any other factors or any other ligands or moisture to come and affect this titanium center. Okay, so the fourth option is the question is between titanium CH3 whole 4 and lead CH3 whole 4, A and B, which of the following options is correct? So A is more stable than B, or A has beta hydrogen atom, or both are stable at room temperature, or B is more stable than A. So the correct option is option D, that is B, that is PbCH3 whole 4, tetramethyl lead is more stable than A. So you know that lead is not a transitional metal atom because lead is coming in the p block element. Lead comes in the region of p block. It is a group 14 metal atom. So it comes in the group 14. There is carbon, after germanium, tin, lead. That's how. But titanium is a 3D metal and it's a group 4 metal. Now lead is a group 14 metal, but titanium is a group 4 metal. It is a p block element, and titanium is a d block element. This is a basic difference between titanium and lead. So you know lead has higher valencies. Lead, since lead atom is quite large in nature, so lead's valency can be expanded to 2 to 4 to 6, etc., etc. But titanium has only 4 coordination number. That is the highest coordination number is the titanium. Now titanium's coordination number is 4, so it is coordinatively unsaturated because titanium can go beyond 4, it is 6, but lead due to relativistic effect cannot go beyond +4 oxidation state. So lead is actually stable at this +4 state. Now, since this titanium has greater coordination number and since only 4 carbon atoms of methyl groups are bonded to it, it is coordinatively unsaturated. Just the example I have discussed in the previous slide, titanium has a coordination number greater than 4 because a d block element, it can go to its octahedral manner also. So 4 to 6 it can go. So it is coordinatively unsaturated in nature. But in case of lead, lead is a p block element and the d orbitals of lead are quite high in nature because the d orbitals are not contracted in case of lead. So the s and p orbitals of lead are quite low in nature, but the d orbital is quite high in nature. That's why lead cannot expand its electron or this valency more than 4. So lead is quite sitting in the +4 state. So that's why lead is coordinatively saturated in PbCH3 whole 4. But in case of titanium, the saturation number is quite less. It is coordinatively unsaturated. That's why B, that is the compound lead, tetramethyl lead, is quite stable than titanium CH3 whole 4. So for information, I have depicted this. The PbCH3 whole 4, that is a compound B, this is at quite a high temperature, 110 degrees Celsius under atmospheric pressure. Though the PVC bond has a smaller force constant, but the titanium CH3 bond has a much larger force constant. Still, it is quite unstable at room temperature. That's why the PbCH3 whole 4 is much more stable than TiCH3 whole 4. Now we're coming to question number 5. There is a decomposition of TiCH3 whole 4. In all the previous examples, I have told you, like in this one also or in this one also, that titanium CH3 whole 4 is quite unstable in nature. Okay, because it decomposes above -40 degrees Celsius, it is coordinatively unsaturated with less bulky methyl ligands. In this case also, I have discussed why the titanium CH3 whole 4 is unstable. But now the question becomes, what's the pathway for the decomposition of titanium CH3 whole 4. The 4 options are given. The first one is the ternary complex formation. Second option is a unimolecular pathway involving TiCH3 bond cleavage. Third option is an unimolecular pathway involving a CH titanium agostic interaction. I have discussed about agostic interaction in the previous slide. You can also Google about it. And the last option is a bimolecular pathway involving a 3C2 electron bond. It's 3 center, C for center, E for electron, a 3 center 2 electron bond. Now the actual answer is decomposition of this TiCH3 whole tetramethyl titanium is possibly proceeding via a bimolecular mechanism. You can see there are 2 titanium atoms are involved. One of the methyl groups we have omitted and we have put this methyl group here, and this methyl is also interacting with other titanium, and this methyl is also interacting with another titanium. So now it's a three center two electron bond, because we are taking each of this set as a three center, this titanium, this carbon, this titanium at a time. So there are three centers, and this titanium, this carbon, this titanium in as a three center. Now there are two electrons are actually shared by both of this carbon and titanium. Here also the two electrons are shared by both of this carbon and titanium. So it is a 3C2E bond in both the cases. Now by weakening of this TiC 2E2C bond by converting into a 2E3C bond. Now, in this case, when this bimolecular mechanism is not operative, the titanium carbon is a two center two electron bond. Actually, one titanium, one carbon. So there are two centers, and there is a single bond between them. So there is two electron. So it is a 2C2E bond in natural condition. But when the mechanism, this mechanism actually applies, the bimolecular mechanism, you see there are three centers, titanium, carbon and titanium, and there are two electrons only, because these bonded electrons are shared by both titanium and carbon, and these bonded electrons is shared by both carbon and titanium. So it's a 3C2E bond. Now from a 2C2C bond you are having a 3C2E bond. So the bond order, that is the increase, this gets decreased from this TiC to this TiC-Ti. That's why if the bond order decreases, we know the compound's strength actually or stability gets down. That's why from titanium CH3 when it proceeds by a bimolecular mechanism, the bond strength gets decreased. That's why the decomposition of titanium CH3 takes place. So take home message from this slide will be, since titanium CH3 is having a 2C2E bond, and by this bimolecular mechanism, it by forming a 3C2E bond, the weakening of the bond occurs because the bond order decreases. This is the actually bimolecular pathway for the decomposition of titanium CH3 Now you can actually argue the fact why the same case is not operative for the case of this compound. That is the compound A, TiCH2CmH3 What's the problem in that? It can also undergo similar fashion of bimolecular fashion, but here you can see these methyl groups are less bulky in nature. But those neopentyl groups, the CH2CmH3 are actually quite bulky in nature. So this transition state is quite bulky or unstable when the methyl groups are substituted by these neopentyl groups. So in case of neopentyl ligands, this bimolecular mechanism is not operative at all. That's why those compounds are actually stable, but this is not. So by increasing the bulk of this alkyl group, we can actually suppress the decomposition of these alkyl titanium compounds. Now coming to the next question, what is the bimolecular decomposition pathway is not feasible for this compound BPY-TiCH3 because the titanium center being coordinatively saturated, coordinatively unsaturated, electronically saturated or electronically unsaturated. Now we have already understood the fact that this titanium CH3 alone is quite unstable in nature. It undergoes a bimolecular mechanism, it is less stable, it is actually decomposed after only minus 14 degrees Celsius. So what are the actually possible pathways that we can stabilize this compound? This is one of the pathway by which we can stabilize the titanium CH3 compound. This is actually a BPY, is nothing but bipyridine ligand. So bipyridine, actually I have shown here two classes of bipyrides are there. One is the 2,2- bipyridine, and this is the 4,4- bipyridine. Now 2,2- bipyridine is where these nitrogen atoms are actually seized to one another, and they can form a chelate, because you can see these nitrogen atoms are quite close to their one another, and it can form a chelate with the metal atom. But in this case, 4,4- bipyridine, the nitrogen atoms are far apart. They're actually 180-degree opposite to each other. So here the bite angle is quite high for this 4,4- bipyridine. So this 4,4- bipyridine is actually not acceptable as a ligand in our coordination chemistry. When we actually denote BPY or bipyridine, this is actually nothing but 2,2- bipyridine. So we will talk about this only. So bipyridine is a potential bidentate ligand. You can see there are two donor atoms, nitrogen. So both nitrogen atoms can each of them donate 2 electrons. So it is a 4-electron donor. Now you can see this titanium CH3 Titanium is in +4 oxidation state. So it is actually +4 means it is D0 system. So methyl groups are actually 2 electron donor. So we have 4 methyl groups. So 4 into 2 is 8. Now pyridine is actually a 4 electron donor. We have shown that's 2 nitrogen atoms. So 2 plus 2 is 4. So 4 plus these 8, actually 12 electrons. So titanium is not, so if it is not having 18 electrons, it is not coordinatively saturated. So it is actually having 12 electrons, it is not having 18 electrons. So it is the option that is electronically it is saturated is not true. So it is electronically unsaturated. Now, though it is electronically unsaturated, it is quite stable, because here you can see there are 4 methyl groups here. So titanium is actually tetra-coordinated in case of TiCH3 whole 4. But whenever we are having a BPY group, the 2 coordination sites of titanium is getting blocked. So from coordination number 4, we are going to coordination number 6. So 6 is the ultimate coordination number of titanium, because we know that D block elements cannot go beyond this octahedral geometry. So this titanium is actually having a hexa coordination around it. So it is coordinatively saturated. So here the actual answer is coordinatively saturated. I am sorry for putting this wrong answer here. It will be actually option A. That is, I have written here option A, but I have put here unsaturation, but it is not. It is coordinatively saturated, because we have seen that bipyridine ligand is having two donor sites block, and we are having 4 methyl groups. So 2 plus 4 having 6. So 6 sites, that is the octahedral geometry around titanium center, is now fulfilled in case of this compound. That's why a bimolecular decomposition pathway is not feasible for this compound. That is quite prevailing is titanium CH3 whole 4. But don't argue with the fact that this is electronically also saturated, because you can see the electron count. This is actually 4 into 2 8 electrons, and it are 4 electrons from bipyridine, so only 12 electrons is there. So titanium is electronically unsaturated but coordinatively saturated. The coordinative saturation is the sole reason for which this bimolecular decomposition pathway is not feasible for this compound. This is the BPY TI CH2 whole 4. Another point, whenever you are taking a ligand as BPY, you will always consider 2,2-BPY, not this 4,4-BPY. Because you see these nitrogen atoms are far apart from one another. These can also act as a 4 electron donor, but since the nitrogen atoms are far apart, so this bite angle or the chelate formation with metal is quite less feasible for 4,4-BPY. That's why this, from ligand perspective in organometallic chemistry, whenever we are talking about BPY, you will think of this, not this. So coming to the next question, this is actually become between two compounds. This is hexamethyl tungsten, and other one is the tetramethyl titanium, the same compound. So WCH3 whole 6 and TiCH3 whole 4. Which one is option is correct? First option is A is less stable than B, or B has beta hydrogen atoms. B is less stable than A, or both are unstable under ambient conditions. So we know from the previous slide that titanium CH3 whole 4 is unstable in nature, and we know that this is actually not having, since methyl group doesn't have any beta hydrogen, so none of these compounds have any beta hydrogen atoms present. Now, so option B and option D are first option correct, that are not acceptable, because we know that both the compounds, none of the compounds have a beta hydrogen atoms, and both are actually not unstable at room temperature or ambient conditions. This is the formation reaction of WCH3 whole 6 I have denoted, because this question also comes in competitive exams, how this forms. So here they have taken hexachlorotungsten, they have treated with methyl lithium in dimethoxyethane solvent, and by transmetallation reaction, this lithium chloride gets precipitated out, and they are obtaining WCH3 whole 6. This compound is comes as a red colored compound and is a trigonal prismatic shape. Now coming to the question, which of the option is correct? Now you see in the first compound, tungsten is coming to the chromium group, chromium, molybdenum, tungsten. Now tungsten has 6 methyl group here, so 6 methyl groups is there, so the coordinative saturation is present in case of tungsten, though it is electronically unsaturated. You see the methyl groups are actually 2 electron donors, so 6 into 2 is 12. But in case of B, this four, methyl groups actually 2 electron donor. So 4 into 2 is actually counting for 8 electrons. This is 12 electron, this is 8 electron. Both the compounds are electronically unsaturated because none of the compounds are 18 electron. But in case of compound B, the coordinative unsaturation is prevailing because there are only 4 coordination number. But here, in case of this compound WCH3 whole 6, the coordination number is 6. So I have already told, like, both A and B are electronically unsaturated, but the coordinative unsaturation is the only one that is accounting for the thermal stability of tungsten hexamethyl 6. So you can see the melting point of compound A is 30 degrees Celsius, so it is quite stable below this 30. It remains a solid. But in case of B, you have already seen that this titanium CH3 whole 4 decomposes only above minus 40 degrees Celsius only. So that's the main reason. The coordinative saturation is the major reason behind the thermal stability of tungsten hexamethyl 6. So now I will be explaining some of the basic reaction examples, how these organometallic reactions will take place. Now the question is, what is the product of the reaction when FeCO5, that is the pentacarbonyl iron. So iron is 0, so it is the iron 0 is D8, 4s2 3d6, that is D8, and 5 carbonyl, so 5 into 10, 5 into 2, that is 10 electrons. So 10 plus 8 is 18, so it is an 18 electron complex. So iron, pentacarbonyl iron, is treated with excess sodium hydroxide. So here I will be discussing such a reaction which will produce carbonylate ion, anion. So what are these? Firstly, from the mechanism you can see we are putting NaOH in the reaction medium. So OH minus is a potential nucleophile. So in this FeCO5, these carbon centers are electrophilic in nature because they are bound to these oxygen atoms. So we know the electrophile and the nucleophile reacts very fast. So what will happen? This OH minus will attack on one of the carbonyl group that is bound to the iron. So now this electron density comes to the oxygen, it pushes it back, and it pushes the electron density on iron. So here we are having this compound. This is a CO4 Fe minus COOH. This is a carboxyl group that is attached to the metal center. Iron is negatively charged because the negative charge on OH is now residing on the head of the iron. Now what happens? The counter anion of this species is sodium, because you see the sodium hydroxide they are providing. So I have treated it as an anion, that is the Fe minus. Now what happens? You see this is the alpha carbon and this is the beta atom. So this is a beta hydride. Now I have already told you about the beta hydride elimination. Any alkyl group which is having a beta hydrogen will undergo beta hydride elimination that can come in a syn fashion or cis orientation to the metal center. So this beta hydrogen gets attached to the iron center and this bond collapses. So this actually gets eliminated as CO2. I will tell you, so any reaction which will have elimination of any neutral molecule, as the olefin or hydrogen or an alkyl group or CO2 or N2O, these are actually very feasible. And you know this CO2 is very stable in nature. So release of CO2, a stable molecule like CO2 from the compound, is actually very favorable. That's why this beta hydride elimination takes place quite fast in this case. So this hydride gets bound to the iron center, this CO2 gets eliminated. So we are having left with this HFeCO whole 4 Na. This is a salt Na plus, and this entire compound is entire ion is minus. Now this minus atom, this minus group, that is a negatively charged anionic group, is actually quite reactive in nature. So these such compounds are, this class of compounds are actually called carbonylate anions. So I have written a line here. What are the carbonylate anions? Carbonylate anions are on account of having a negative charge on the compound and is a negative charge on the metal center, and they are having a hydride. Hydride is a very strong electron donor. So the electron density of this anion is very high. So this, due to this accumulation of very high negative charge on the species, and since metal atom is already negatively charged, you know metal atoms are actually prone to have a positive charge upon them. But if you are having a negative charge on a metal, it is quite unstable and it is quite reactive in nature. So this reactive species is actually basic in nature and it acts as a potential nucleophile. Now you see this is an iron hydride. So this is an iron hydride. Now this iron hydride is there, and we are putting excess NaOH here. So not 1 mole but 3 to 4 moles of NaOH is there. So another OH minus will come into picture. So OH minus is also a strong nucleophile, and it can also act as a base. So OH minus will abstract this proton. This is quite acidic in nature for it. So it will abstract this hydrogen as proton, and it will be eliminated as H2O. So this is also a neutral molecule that is quite eliminated in this reaction pathway. So firstly the CO2 gets eliminated, and lastly this H2O gets eliminated. So now this OH minus is having the H plus away from the center, so it will have put another negative charge on the metal center. So this will become FeCO4 2 minus, or we can write it as a Na2 FeCO whole 4, or you can, so 2 Na plus is there and 1 FeCO4 2 minus is there. So we'll again count the electron count of the species. Iron 2 minus is there, so iron 0 form is D8, 2 minus is 2 more negative ions is there, so 8 plus 2 is 10, and from this 4 carbonyl moiety we are having 8 electrons. So 10 plus 8 is accounting for an 18 electron. So this entire species is also a very stable species, that is 18 electron. This is popularly known as a Coleman's reagent. You can Google about this Coleman's reagent. It is a potential nucleophile, and it is actually heavily used in organometallic chemistry. So thus, by a commercially available reagent FeCO whole 5, by treating it with excess sodium hydroxide, we can form this compound, that is the Coleman's reagent. So here firstly the nucleophilic attack of the OH minus takes place on carbon with elimination of the CO2. Now we are having this compound, and now from acid base reaction between this acid and this base, with concomitant release of H2 or water molecule, we are actually arriving at Na2 FeCO whole 4, that is nothing but the Coleman's reagent. Now coming to the next reaction, what is the product when tantalum pentachloride is treated with? Firstly, there is the ZnCH2 tert-butyl whole 2. This is a neopentyl ligand. I have already discussed what is neopentyl ligand, without devoid of any beta hydrogen. And lastly, it is treated with lithium CH2 tert-butyl lithium neopentyl. So firstly, this is a actually specific class of reaction, that is alpha elimination. You have actually heard of beta hydride elimination. I have discussed lots of examples on beta hydride elimination before, but it is actually nothing but the alpha elimination. Now what happens? The first reaction is, I have already discussed about transmetallation reaction, where two of the metal centers actually switch their corresponding ligating atoms. Now we are having this neopentyl ligand, and we have this Cl. So now we know that ZnCl2 is a very stable molecule. So Zn plus 2 will abstract 2 chlorine atoms from tantalum Cl5. So tantalum is left with 3 Cl atoms, and we are having left with this tantalum CH2 tert-butyl whole 2. Okay, so now we are having this compound. So by transmetallation we are having this. Now this compound I have abbreviated here. Okay, so now is one of the Cl atoms will be, now this we are adding this LiCH2 tert-butyl compound. So these are having is a main group organometallic compound. This CH2 minus get attacked on this, and one of the Cl atoms get eliminated. So we are having an elimination of LiCl, and this CH2 tert-butyl gets attached to this tantalum. So for ease of understanding, I have actually bracketed these 3 neopentyl atoms in groups in one case, and here I am showing only one neopentyl atom. So you see these are alpha hydrogens, but in the beta position there is no hydrogen atom present. We are having one chloro. Now in this case the alpha hydrogen abstraction takes place. Now since we are having this reagent in excess, and this compound is also can also act as a base, so this CH2 minus tert-butyl actually abstracts one of the hydrogen atoms. This bond collapses to this, and this elimination of Cl takes place. So there is forming a tantalum carbon double bond here, and since this CH2 minus is abstracting this proton, it is becoming an alkane. This alkane is nothing but CMe3 whole 4. That is one carbon atom bonded to 3 methyl groups. And also this Cl minus gets eliminated, that is actually captured by the lithium plus. So also we are having a elimination of lithium chloride. So from this if we add this CH2 minus tert-butyl group, it will abstract this alpha proton because it is not having any beta hydrogen. This bond collapses. A tantalum carbon double bond is there with the tert-butyl group attached group, and now this is actually hydrogen atom, one of the hydrogen that is not eliminated, and we are actually left with tertiary butyl CH2 whole 3 tantalum double bond, this H and tert-butyl. So this is the very classical example of alpha hydrogen abstraction, when we are not having any beta hydrogen atom and we are putting such a strong base like lithium CH2 tert-butyl is a nucleophile as well as a base, then we are actually left with elimination of LiCl and a stable alkane molecule Me4, and we are having this carbene type of compound, tantalum carbon carbene. So the next question is another, we are coming back to the beta hydride elimination. What is beta hydride elimination? So two sets of compound I have taken. Firstly is the metal norbornyl whole 4. Secondly is the metal aryl whole n. This n can be anything. So here I have depicted metal atom coordinated with 4 norbornyl groups. For information, I will ask you to go through this group once. You can Google about this norbornyl group. This is actually norbornyl group. This this compound is actually called norbornyl group. Norbornyl group is actually not having the beta hydride elimination. The beta hydride elimination in case of this is actually not very much feasible. So why it is such, I will discuss with you. You see, in this case, this is the metal. So this is the alpha carbon, and we have 3 beta carbons here. One is this, one is this, and another is in the bridgehead position. So for your example, for your information, I will tell you that these carbons are actually called these 3, 1, 2, and 3. These 3 carbons are actually called bridgehead position because this, you can see, this is a bridge, and these are actually on the head of the bridge. So these are actually called bridgehead carbon atoms. So they are actually having 2 hydrogen atoms here, 2 hydrogen atoms here, and 2 hydrogen atoms here. So we are having 6 hydrogen atoms from each non-Bornyl group, though it does not undergo any beta hydride elimination. Because if in any of the hydrogen atoms beta hydride elimination takes place, double bond will be occurring here between this carbon and this alpha carbon and this beta carbon. Now, so the product will be metal hydride containing 3 non-Bornyl groups, and we are having this alkene molecule which is having a double bond in the bridgehead position. Now here comes a Bread's rule. I have depicted here what is Bread's rule. You can Google about it. Bread's rule. What is Bread's rule? Bread's rule states that it does not allow to put any planarity on the bridgehead position of any non-Bornyl group or any other group which is a bridgehead position. Bridgehead is this position, this position, this position. These are not bridgehead positions. So why the Bayes rule states that there cannot be any planarity in the bridgehead position. So you see, this is actually, this is not on plane. This is actually like this. This is actually like this, and on top of this, a kind of cone is there. So if a cone is there, and so this does not allow this carbon-carbon hexagonal plane to come in the planar conformation. So it actually allows it to a twisted fashion like this. So if it is twisted, so the attainment of planarity is not possible or less feasible in case of non-Bornyl group. Here also, no carbocation can also form because carbocations are also planar in nature, and this bridgehead actually molecule is not allowing it to come to the planar system. That's why attainment of positive charge, that is carbocation, or attainment of double bond, that is the olefin, all are not actually feasible in case of such non-Bornyl group. That's why this process or this production or the generation of such olefin from this group is quite not feasible. So if this product is unstable, so this forward reaction will not be feasible at all. So the backward reaction will be more favorable, and this molecule will not undergo, is reluctant towards any beta hydride elimination because bridgehead position, at bridgehead position and beta hydride elimination cannot occur because at this bridgehead position no attainment can be of polarity can be done. So this olefin is actually very much strained in nature because it is like this, and this attainment of polarity is not possible. If it were like this, In a planar system, like my hands are actually connected to one another, then it would be stable, so beta hydrogen elimination would take place. But here this system is here because one of the carbon atoms CH2 group is actually pressing this plane to its downward manner. That's why attainment of planarity is not possible in such cases. Now coming to the second option, that is the metal aryl cases. So what is the aryl group? Aryl group is nothing but the benzene group. So here you can see that beta hydrogen atoms are present, two beta hydrogen atoms, and if we can perform the scheme of beta hydrogen elimination, we are left with a metal hydride and a carbine. And you can see like carbine molecules are really unstable in nature, because in this carbine system we are having orthogonal p atoms which are having negative charge side by side. Now, since these metal complexes have been produced such an from this aromatic complex to such a non-aromatic complex, so this forward reaction is also very much less feasible in nature. That's why the beta hydride elimination is not also possible in case of metal aryl groups. Such is also possible in case of metal acetylide groups also, MC triple bond C groups also. These would also undergo any beta hydride elimination. So metal non-bondanyl groups, metal aryl groups, metal ethylene groups, or metal acetylide groups, they are not actually prone towards any beta hydride elimination. So this is another reaction. This is one of the compounds, that is NaMnCO whole 5, Na plus and MnCO5 minus, when it is treated with a allyl halide. This is a allyl halide. This group is called allyl. This is the carbon-carbon double bond and carbon single bond is attached to an X. X is nothing but any halogen or pseudo halide halogen group, that is Cl or Br or I or OTF or OBF or ONS. And the second parameter is given as the H nu, that is the light. So what happens when this compound Na plus MnCO whole 5 is treated with firstly an allyl halide and this H nu. This is the energy or light. Now MnCO whole 5 minus, Mn is actually a 78 system, Mn minus. So and we are having 5 carbonyl group. So 5 into 2 is 10 electrons, 10 plus 8 is 18. So this is an 18 electron complex. Now MnCO whole 5 minus, when it is treated with this, what will happen? So in some previous slides, I have already discussed in this slide, I have told you these such kind of molecules, when a metal atom is having a negative charge on them, is actually quite strong nucleophile, because it has a lot of electron density on the head of the metal. Same also holds for this compound, because here the metal atom is having a high negative charge density on it, and so it will be an SN2 type of reaction when this carbon atom will be attacked by the negative charge on the manganese. So we are having a metal allyl complex. So manganese will be bonded to carbon with release of this NaX, that is the salt, and now we are having CO5Mn bonded to carbon single and CC double bond. It's the allyl group. But now since the carbon atom is actually bound to only the metal manganese atom is actually bound to only one carbon atom of the allyl group, it is an eta 1 allyl group. Here you can count the electronic configuration. Here manganese was minus, but here manganese has gone to +1. This is actually Ampolang reaction. You can have Google about the what are the Ampolang reactions. Ampolang reactions are nothing but reversal of the polarity. Here manganese was negatively charged, but here you can see the manganese carbon bond is charged, so it is positively charged. So from minus or negative, we are going to plus, that is positive. Now this is the eta 1 allyl complex. Now eta 1 allyl complex, we can count the electron is a 2 electron donor, and this MnC and CO5 are actually 5 CO atoms are actually 10 electron donors. So 10 plus 2 is 12, and manganese 1 is D6 system, so it is actually 18 electrons. So from 18 we are actually obtaining an 18 electron complex, eta 1 allyl complex. Now this eta 1 allyl complex, we are putting H nu, that's light energy. For information, I will tell or suggest you, whenever you are seeing a manganese or any metal CO metal carbonyl complex, and if we are enlightening it with some wavelength like H nu, like a blue light or green light, the one of the CO molecules will get departed. So now if one of the CO molecules get departed, COs are actually photolytically unstable, they will release from the metal atom. So we are having one CO4, and we are having a manganese, and now the eta 1 allyl group will be transforming towards the eta 3 allyl group, when all the carbon atoms are actually involved in binding to the metal atom. We know eta 3 allyl groups are actually having 4 electron donor capacity. So we are having 4 from the CO, 4 into 2, that is the 8 electrons from the CO, 4 from this eta 3 allyl, that is 12, and from manganese 1 we are having a plus a 6 electron count. So 12 plus 6 is counting towards 18 electrons. So from 18 electron we are actually arriving at 18 electron, but through such kind of transformations. Here, since one of the CO molecule is released, so manganese actually allows this eta 1 allyl to move to the eta 3 allyl to remain its electron density, electron count intact. Here we are having an 8 electron compound. 18 electron, if one of the CO molecules gets eliminated by the allowment of CO, we are having a 16 electron complex. Since 16 electron complexes are less stable than the 18 electron complexes for manganese, then it will allow this eta 1 allyl to form an eta 3 allyl, so that from 2 it will be actually having 4 electron donorship. Then it actually again forms the 18 electron count. These are actually called ring slippage reactions, where the donation mode of the ligand actually gets changed according to the environment around the ligand center of the metal. Here, since one of the CO is eliminated, the allyl group has actually transformed itself from eta 1 to eta 3 to maintain the electron density of the manganese 18. So now this question is actually is the difference, what is the stretching frequency differences of the CO group in the following molecules. You see both are the tungsten molecules. We are having ancillary ligands as PMe3 groups and Cl groups, and we are having a PHC double bond group, that is a carbene complex, and we are having a PHC triple bond tungsten, that is a carbine complex. So here you can see the new CO, that is the highest stretching frequency of CO here is 1938, but in this case the CO frequency is only 1870. So quite a 70 centimeter inverse increment in CO stretching frequency is there. So the stretching frequency is nothing but the strength of the CO. So we are actually having an account that this CO bond in this compound is quite stable than this CO bond of this compound. So we have to rationalize why this is happening. So here I have actually shown an example. Whenever a metal atom is actually bonded to a CO molecule, it will undergo a resonance structure like this. The metal atom's electron density will be pushed towards the pi star of the CO, and thus the resonance structures you can see the MC single bond and C triple bond O. So it will be MC double bond and C double bond O. Left hand side you can see this is a triple bond character of the CO and is a single bond character of the MC bond. But here on the right hand side you can see that is a double bond character of the MC and double bond character of the CO. So from a triple bond character of CO with the electron pushing towards the CO, we are having a double bond character. So for bond order 3 is going to bond order 2, and here from bond order MC bond order 1 we are going to bond order 2. So MC bond is actually getting stronger when the back donation from the metal to CO takes place, and the CO bond actually gets less stable or its stretching frequency decreases when the back donation takes place. That's why, since it is having the back pi donation of electron from the metal center, this is a carbine and this is a carbene. So carbines are actually more electron rich, so it will push its electron density on the metal center more. So this tungsten is actually electronically more rich, so it will actually throw its electron more on the CO, so the CO stretching frequency will drop more down. But in case of these, the carbines are actually less electron pushing on the metal. So in this case the electron density on the metal center is not as much in this case B, so it will push this electron to the CO less. That's why in this case the new CO remains high. So the more back pi donation from the electron of the metal center, the more will be the electron density on the metal, the less will be the bond strength of the CO. So in this case, since carbines are actually electronically more rich than carbene, that's why in this case the electronically push to the CO will be more in case of B than that of A. That's why the new CO in this case is actually quite less, but in this case the new CO is quite high. So for example, you can actually change in the questions like what are the other kind of ligand which are more electrically each. So when the electron donating ability of the ligand is more, you will see the stretching frequency of the CO gets decreased. And when the stretching frequency here, if we are having a electron withdrawing group, then the stretching frequency will be more of CO. So that's how the questions might be framed. This is the last question of this session. When it is though cyclobutadiene, that is a C4H4, is highly unstable and readily polymerizing in its free state, its transition metal complexes can be isolated, because the first option is it engages in long range interaction with the transition metals. Second option is it becomes stable by forming C4H4 plus in presence of transition metals. Third option, its polymerization ability reduces in presence of transition metals. And the last option is it gains stability due to the formation of C4H4 minus on binding to transition metals. Here I have actually drawn the examples of Huckel's rule of aromaticity and anti-aromaticity to answer the question. Here you can see this is a free cyclobutadiene molecule. We are having two pi bonds, so we are having 4 electrons here. So 4 electrons is nothing but foreign number of electrons according to Huckel's rule is anti-aromatic in nature. And anti-aromatic compounds are actually highly unstable. We all know. But whenever we have a transition metal, suppose it is residing in its X oxidation state. Now we know transition metals are actually reducing in nature. So it will reduce this cyclobutadiene by putting another two electrons on it. So it will be oxidation state will be plus 2 than the previous one. So it will be Tm x plus 2, and now it will be acting as a di-negative anion. So from C4H4 it will be C4H4 2 minus on binding to the transition metal. Now this negative charge can undergo free resonance with this entire ring, and you can see there are 6 electrons. So here it is 2, and here are 2 to 4. 4 to is actually having 6 electrons. So now the 6 electrons according to Huckel's rule is coming to the 4n plus 2, where n is equal to 1. So 4n plus 2 is 4 into 1 plus 2, so 6. So 6 electrons are present in this complex. So in this case, it is actually having anti-aromaticity. From anti-aromaticity, it is having aromatic character. So aromatic characters are quite stable in organic chemistry. Aromatic molecules are quite stable in organic chemistry. So that's why this complex can be isolated now. So from anti-aromatic character in presence of metal, it is actually going to the aromatic character. That's why though cyclobutadiene is quite unstable, its complexes with transition metals atoms are quite stable in nature. That's why their complexes can be isolated. So the correct option is option D. That is, it gains stability due to the formation of C4H4 minus on binding to the transition metal atoms. So here I will end my session. Now it is upon you. So if you have any such question or on any slides, I'll be happy to answer. So you can go on with your question. If you have any doubt regarding any of the question, you can ask.